Hello everybody. Welcome back to Calculus 1 online at Frederick Community College. In this video, we will discuss limits at infinity of polynomial and rational functions. Let's consider the following function, f of x equals to 1 over x plus 3. We know what this function is. This is a reciprocal function that is shifted 3 units up, and it is shown here on this graph. Okay, and now we're going to consider the behavior of this function as x gets really large in magnitude. Okay, so here is a table of values, something that we've done at the very beginning of our class, except now our x gets really big. So I started with 10, then it increased to 100, 1000 and so forth. And notice what happens to the values of the function. They are getting closer and closer to 3. And of course, on the graph, this corresponds to this right branch that it is approaching this horizontal line, y is equal to 3. Okay. Now, what if we let x go to the left side, right? So it's still going to get really big in magnitude, except now it's going to be negative. So this is what happens here. I start with negative 10, then negative 100, negative 1000, and so forth. And notice that the values of the function also get close to 3, which is coming from a different side. And this corresponds to this branch right here. Okay, it is also approaching y is equal to 3. It's just coming from a different side, but this is what we refer to as limits at infinity. That is the behavior of the function as x gets really big in magnitude, whether it's going to positive infinity, so that x for positive values, or negative infinity whenever x has negative values. And in the limit notation for this particular function, we would say that limit as x goes to infinity of f of x is equal to 3. And limit as x goes to negative infinity of f of x is also equal to 3. You can see it from the table. You can see it from the graph. So this is just a motivational example to kind of get us started and show us what we're going to discover in today's lecture. Okay, so now we can define what a horizontal asymptote is in terms of limits. We say that if the limit of f as x goes to infinity is equal to L, or if the limit as x goes to negative infinity of f of x equal to L, we say that the line y is equal to L is a horizontal asymptote of f. Now, why did I highlight that or? This is just to emphasize that this statement says that either one of the limits or both. Okay, so here's one case where we have a horizontal asymptote at what value? So this would be y is equal to 4. And notice that both limits, as x goes to positive infinity and negative infinity, both limits are the same. Okay, in fact, in this case, both branches are approaching 4 from the same side. Okay, now here's another example where we only have one limit. So this is an exponential function. Okay, e to the x plus 2, and which limit do we have here? This would be the limit as x goes to negative infinity. Okay, and we can see that this limit is equal to 2. Okay, so limit of this function as x goes to negative infinity is a fixed number. Okay, notice that as x goes to positive infinity, the limit doesn't exist, right? Because the branch goes up to infinity. All right, but we still have a horizontal asymptote, and that asymptote is y is equal to 2 for this particular example. So I just wanted to show you two examples where the limit connection is somewhat different, right? So for the first example, the two limits exist. For the second example, only one of the limits exists, and we still have a horizontal asymptote. Now let's switch our focus to the discussion of limits at infinity of polynomials, which boils down to just looking at the and behavior of these functions. Let me go ahead and highlight this phrase right here. The and behavior refers to how the functions are acting as x gets really large in magnitude, whether it gets really large with a positive sign, in other words, going to positive infinity, or large with a negative sign, so that corresponds to negative infinity. Now here you see a general form of a polynomial function. So we have coefficients that go with x terms, and we have n minus 1 and so forth. Those refer to the powers of x, and those numbers need to be positive integers. So this is just a simplified definition of a polynomial function. And the good news for polynomial function is that there are only 4 scenarios to consider, and the and behavior of polynomial function depends on 2 things. So it depends on the degree, whether it's even or odd, and then it also depends on the sign of the leading coefficient. So I'm highlighting this term here, a sub n, that refers to the leading coefficient. Okay, that's the number that is attached to the x term with the highest power. Okay, so we're going to abbreviate it as LC, corresponding to leading coefficient. So let's take a look at these 4 scenarios. We have even degree positive sign that corresponds to the leading coefficient sign. So let me put a plus here. Even degree negative sign. Then we have odd degree positive sign for the leading coefficient and odd degree negative sign. Okay, and those are the only 4 scenarios, or 4 things that can happen to a polynomial. All right, so now we can think about simple functions that correspond to these scenarios. And here they are. All right, so even degree positive sign, the easiest function to consider for this scenario would be x squared. We are very comfortable with this function. We know all their properties. So that is what I would think of as a polynomial to keep in mind for even degree and positive sign of the leading coefficient. Okay, what about negative sign and even degree? Well, let's go ahead and flip that parabola. So that would be negative x squared. And we know very well how to graph this function, how it behaves, and so forth. Okay, what about odd degree positive sign? Well, you might have guessed this is x cubed. Okay, odd degree negative sign, that would be negative x cubed. And just by looking at the and behavior of these functions, we can make a conclusion about the limits of all polynomial functions that fall into one of these categories. Okay, so for the limits, what happens? For polynomials of even degree with the positive leading coefficient, the limit as x goes to infinity is infinity. Okay, and that corresponds to this branch right here, goes up to infinity. The limit as x goes to negative infinity is also positive infinity, and that corresponds to this branch right here. So what does that mean? That means that all polynomials of even degree with the positive sign for the leading coefficient act the same way at infinity. Okay, stuff in the middle might be different, but at infinity we have this. Okay, what about even degree negative sign? We have the following. Look, both of the branches are going down. So as x goes to infinity, the limit is equal to negative infinity. As x goes to negative infinity, the limit is also negative infinity. Okay? For odd degree, positive sign, one branch goes up, one branch goes down. So that corresponds to the following. Limit as x goes to infinity is equal to positive infinity, and limit as x goes to negative infinity is negative. Okay, and let's finish off our last case. So that would be negative x cubed. So that corresponds to all polynomials of odd degree with a negative leading coefficient. Notice now the left branch goes up. So that corresponds to what? That would be this limit right here. Limit as x goes to negative infinity is equal to positive infinity. And then the right branch goes down. So that would be the other limit. Okay, so this is a nice diagram to keep in mind as we are computing limits at infinity of polynomial functions. All you need to do is to determine the degree of your polynomial and also look at the sign of the leading coefficient. And that's what we're going to do on the next slide. Now that we have seen the four scenarios for and behavior of polynomial functions, let's take a look at some examples. So the first example says negative 3x cubed plus 2x minus 4. So I need to identify the degree of this function. That would be 3, the highest power of x. And then the leading coefficient is negative 3. It is negative, and that tells me which case to consider. So this is the behavior of a function with an odd degree and negative leading coefficient. So what happens here? The limit of this function as x goes to positive infinity, that will be negative infinity. Okay, how do I know? I think about negative x cubed, which looks kind of like this. Okay, so that's negative infinity. That's the behavior of this function as x gets really large. Okay, what about as x goes to negative infinity? Then the branch goes up, so that would be positive infinity for the end behavior. And what is my reasoning here? The degree is 3, that's odd, and the leading coefficient is negative, right? So negative leading coefficient, odd degree, we know how those functions behave. And now let's take a look at the graph of this particular function. Okay, so the graph of this function is over here. You can see that our conclusion is correct. Okay, so that's our first example. Let's take a look at the next example. Here we have 4x to the 6 minus x cubed plus 2x minus 1. Okay, once again, what am I looking at? I'm looking at the degree. So the degree is 6. Leading coefficient is 4. Okay, what type of function should I keep in mind as I think of the and behavior of this polynomial? I'm thinking about our parabola. So parabola that opens up. Both branches go up to infinity. That means my limit here will be infinity and also over here. Okay, what is the reasoning? The degree is 6. That is even. The leading coefficient is 4, so the sign is positive. The and behavior will be of this type. Okay, and let's take a look at the graph of this function. And there it is. So this function right here. Okay, you see that both branches go up to infinity. Stuff in the middle is different, no problem there. We're only looking at the and behavior of these functions. Okay, two more functions, right? So let's take a look at the third example. X to the 5th minus 3x squared minus 2. The degree here is 5. The leading coefficient is 1. It is positive. So let me write it out over here. The degree is 5. That's odd. the leading coefficient is 1. All I care is the sign, so that's positive. What is the function that I should think of? Okay, x cubed looks kind of like this. So what does that mean? Well, as x goes to positive infinity, the branch goes up to the right. Okay, so that would be positive infinity for the limit. And for negative infinity, it goes down to the left. So that would be negative infinity for this limit. Okay, let's take a look at the graph. There it is. So you can see again the stuff in the middle, right? The behavior of this function kind of in the middle. That's going to be different for all of these functions, but the end behavior will be the same. Okay, one more. We have negative x to the fourth minus 2x squared plus 7. So what do we got here? So the degree is 4. So that's even. Okay. And the leading coefficient is negative 1. So that's negative. Okay. What should I think of for this particular function as kind of like a model? Well, that would be negative x squared. We know what that looks like. That is a parabola that opens downward. Okay. So both limits should be negative infinity. I'm going to put over here. Then let's check the graph, and there it is. Okay, so that's it. That's all the cases that we can consider for the polynomial functions. Again, just to emphasize, all you have to do is take a look at the degree. Okay, figure out what the degree is. Now, be careful. Sometimes the way the homework is written, that leading term might not be the first term in the expression. So really look at your function and pick out the highest degree term. Okay, and then look at its coefficient, right? All we need to determine is whether it's positive or negative, and then you refer to the model function that shows you the behavior of this polynomial. Now let's switch our focus to computing limits at infinity of rational functions. Let me give you a quick reminder of what rational functions are. We say that f of x is a rational function if we can write it as a quotient of two polynomials. And for our notation, we're going to say p of x is the polynomial in the numerator and q of x is the polynomial in the denominator. Now let's say a is the leading coefficient of p and b is the leading coefficient of q. That's going to be important in determining some of the limits. Okay, so now let's take a look at the following cases. We are going to compute limits at infinity of rational functions by considering these three scenarios. First is when the degree of p is equal to the degree of q. That's probably one of the easiest cases to consider. The limit as x goes to infinity of that function, whenever the two degrees are the same, is going to be computed by a over b. And the same is going to be for the limit as x goes to negative infinity. For the time being, just remember this expression. Once we take a look at some examples, you will see why that is the case. Okay, so again, when we have two polynomials for our rational function and their degrees are the same, we just take the ratio of their leading coefficients, and that's going to be the limit. And here's just a quick example of what that might look like. This is a rational function, and you can see how both branches are approaching the same value. Okay, now you're not given here an actual expression for the function, but just trust me that this is a rational function where the asymptote, the horizontal asymptote, is computed by taking their leading coefficient and dividing them. Okay, so first case done. Second case, when the degree of p is less than the degree of q. That is also a nice case to consider, because here we're just going to say it's going to be 0 for both limits. Okay, and again, we will see why that is true once we take a look at some examples. Here is a quick example of a function where the degree on top is smaller than the degree on the bottom, and you can see how the two branches are approaching zero. They are coming from two different directions, but we do have a horizontal asymptote here, and that is y is equal to 0. Okay, and then the last scenario, when the degree of p is greater than degree of q, that one is a little bit trickier. To make this as a general rule, this is going to be plus minus infinity for both, and we're going to have to do a little bit of work trying to figure out which infinity it is. So I'm giving you one example here. So for this particular problem, what we have is the degree of p is greater than degree of q, and we have a slant asymptote. That happens when the degree of p is greater than degree of q by exactly 1. Okay, so what happens here, you see that the right branch goes up to the right. Okay, so this is going to correspond to the limit as x goes to infinity is going to be positive infinity. Okay, and the left branch is going down to the left. So as x goes to negative infinity, that's going to be also negative infinity, but that's just one example. So as always, you can use Desmos to compute these limits, okay? But we're going to learn how to compute these limits algebraically, okay? All right, so these are the three cases that you should keep in mind as we approach limits at infinity of rational functions. Okay, let's take a look at our first example where we would like to compute the limits at infinity of the following rational function. F of x is equal to 2 minus x squared over 3x plus 2x squared minus x cubed. So here is my solution. Okay, I broke it down as the quotient where p of x has degree 2. Okay, so my polynomial in the numerator is of degree 2. Q of x is of degree 3. So this is the case where the top polynomial has a smaller degree. Okay, that means we have a horizontal asymptote y is equal to 0. So just from here, we can conclude that the limits, both as x goes to negative infinity and positive infinity, are going to be 0. And you can see that on the graph over here. So here's this branch approaches the x-axis as x gets really, really big. And on the left side, same behavior. Okay, it's approaching from a different direction, but it is going to 0 as well. Okay, now alternatively, we can compute these limits algebraically by doing this trick. We're going to multiply our function by the following expression: 1 over x squared over 1 over x squared. Or you can also think about it as divide both top and bottom by x squared. And what you're going to do for problems like this, we're going to pick the highest power in the numerator. Okay, so I pick that value right here, and you'll see why. So once I multiply the numerator by 1 over x squared, what's going to happen? I'm going to get 2 over x squared minus 1 over x minus 1. Okay, and on the bottom we get 3 over x plus 2 minus x. This is what we get over here once we do the algebra. And now if we evaluate our limit as x goes to either positive or negative infinity, what's going to happen here? Well, as these values get really, really large in magnitude, this is going to go to 0. This is going to go to 0, right? And so is this number right here. So you can think about it as the following. Now what you have is negative 1 over 2 minus x. Okay, that's what we have left over as x gets really, really, really big. But what happens now in the denominator? That's a really large number, either positive as x goes to positive infinity or negative as x goes to negative infinity. But either way, that's going to give us 0 because -1 divided by a large number in magnitude, okay, is going to be 0. Okay, so that's how you would approach this type of problem algebraically. And as you work through problems on your homework, that's what the approach is for their explanation. Okay, you will notice that they're going to break it down just like I did here with a little bit more detail. So they really go out of their way to show all of the steps, how they divide each function by x squared and show all the work. So you might be asking, which method should I go with? Well, you can just stick with this one right here and say, oh, the degree on top is less than the degree on the bottom. Then we have y is equal to 0 as our horizontal asymptote. So we can conclude from here that the limits are equal to 0. Okay, or if you like to do algebraic manipulation, you can follow this trick right here. And bottom line is you should get exactly the same answer, whichever method you apply. All right, let's take a look at the next two examples where we have the same degrees on top and the bottom. So first we have f of x equal to 3 plus x cubed minus 5x over 4x plus 3x cubed. And notice that here I am using Desmos to graph my functions. I like doing that, so I always confirm graphically that my answers are correct. So what's going on here? The degree of the function in the numerator is 3, and the degree of the function in the denominator is also 3. Okay, so this is the case where the degrees of two polynomials are the same. Let's take a look at our solution. So here I'm writing out that degree of P is equal to the degree of Q, and it is 3. Notice that in both cases, that term, the leading term, is not listed first, and this is what I was referring to earlier. It's not going to be the first term that's listed, right? You really need to take a careful look and pick the one with the highest power. So from here we say, okay, we must have a horizontal asymptote at 1 over 3. So the limit should be 1 over 3. And you can see it right here from the graph that, yeah, it does look like it is 1 over 3. Okay, or we can apply our algebraic trick. So multiply by 1 over x cubed over 1 over x cubed, or the same as saying divide by x cubed, both top and bottom. Okay, so let's work through this solution here. As we multiply the top by 1 over x cubed, what's going to happen? We're going to get 3 over x cubed plus 1 minus 5 over x squared. Okay, and on the bottom, we get 4 over x squared plus 3. So what's going to happen as x goes to either positive or negative infinity? These terms right here, they vanish, right? So this goes to 0, this goes to 0, and this. And notice what we have left is just the leading coefficients, right? Okay, 1 over 3, that's what we have left. Okay, so in this case, what is the strategy for the algebraic solution? You would divide by the highest power. Okay, and because it is the same, what's going to happen? Most of your terms will vanish, and we're just going to be left with the leading coefficient. So 1 over 3, that's our limit. And so we showed it algebraically, we showed it with the graph, we also showed it by just looking at the degrees and saying, yeah, okay, if we have those degrees the same, we just do the division. Okay, so that's our first example. Let's take a look at the next one. Here we have another type of function, Okay, we have negative 4x squared plus 3x cubed on top, 1 plus 5x squared plus 2x cubed on the bottom. And here is my solution. So I'm just going to stick with the quick version of it. The 2 degrees are the same. Okay, so I have a horizontal asymptote, y equals to 3 over 2. So here's my leading coefficient for P. Here's my leading coefficient for Q. Okay, so that means the limit of f of x as x goes to both positive and negative infinity is 3 over 2. And Desmos does confirm that. Okay, so here's my right branch approaching this value as x gets really big. And the left branch also approaches the same value as x goes to negative infinity. If you would like to practice, you can try this approach right here by multiplying this function by the same expression, actually, because the degrees are the same, right? So 1 over x cubed over 1 over x cubed, you will see that you're going to get exactly the same answer. Okay, so this case, when the degrees are the same, is nice. All we need to look is the leading coefficients. And again, if you would like to do the algebraic step just to verify, you're certainly welcome to do it. And always, 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 Desmos is a nice way to check your work. Quickly plug that into your Desmos. Make sure that the graph tells you the same story as your algebraic solutions. Okay, let's take a look at our last examples for this lecture. And these ones are a little bit tricky, and we have to be very careful as we analyze these type of functions. So this is the case where the degree on top is bigger than the degree on the bottom. And here we would have to apply that trick of multiplying or dividing by some expression of x. Okay, so here's my first problem. Negative 3x to the fourth plus 4x squared minus 5x. That's the polynomial on top. And the polynomial on the bottom is 2x squared minus 5x plus 3. Okay, so what do we have here? The degree on top is 4. It is bigger than 2. So here we must do the algebraic step to determine what our limits are. Okay, so we're going to multiply our function by 1 over x squared, divide by 1 over x squared. Okay, so we're basically taking the degree of the polynomial in the denominator. Okay, so once we multiply this through, what's going to happen? On top, we're going to get negative 3x squared plus 4 minus 5 over x. And on the bottom, we're going to get 2 minus 5 over x plus 3 over x squared. Now, as x gets really big in magnitude, right? So it either goes to positive infinity or negative infinity. These terms right here, they will vanish. So negative 5 over x, that's going to vanish. And also 3 over x squared, right? So all of these terms are gone, okay? So now you can think about it as the behavior of this function just with the terms that are left. So negative 3, and here I'm using not very rigorous notation. Say negative 3 times infinity square. I'm not really plugging infinity. I'm just thinking of the behavior of this function as x gets really, really large. So negative 3 times infinity square plus 4 over 2. What does that look like? Well, okay, if I take a really large number and I squared, it's still really, really large, and then I multiply it by negative 3, that's where negative comes in, okay, negative infinity. That is the behavior of my function as x goes to positive infinity. Same idea for x going to negative infinity, okay? If I plug it in over here, that's going to get rid of the negative sign, okay? But then I still multiply it by negative 3, Okay, so my answer is the same. This would be negative infinity, and that corresponds to our graph over here. Okay, so the left branch goes down to the left, the right branch goes down to the right. Okay, the two limits are both negative infinity. Okay, so again, for problems of this type, we will need to solve them algebraically by doing this trick of multiplication by an expression of x. And then, of course, you can always check your work with Desmos. All right, let's take a look at one more problem for this lecture. Here I have negative 5x to the fourth minus 3x to the fifth minus 3x. That's the polynomial of fifth degree in the numerator. Okay, and then I have negative 4 minus 3x to the fourth. That's the polynomial in the denominator. Okay, let's see what our solution is going to look like. So 5 is greater than 4. All right, so this is the third scenario that we've discussed. We need to multiply our function by 1 over x squared, x to the fourth over 1 over x to the fourth. Okay, so here you see the solution. All right, I carefully multiply my top and bottom. And once I simplify, I get this. So I kind of rewrote it a little bit. Negative 3x minus 5 minus 3 over x to the third power. And that's going to be the term in the numerator. And in the denominator, we get negative 3 minus 4 over x to the fourth. And notice that these terms right here, they're going to vanish as x goes to either positive or negative infinity. So now I can just look at the behavior of my function and how it behaves if I just plug in a really, really large number, okay, into this expression. So negative 3 times infinity minus 5 over negative 3. Okay, so what happens here? It's a really large number multiplied by negative 3 minus 5, and then divide by negative 3. Okay, so there are two negatives, one on top and one on the bottom. They cancel out, and this is where we get positive infinity. And you can see on the graph, this corresponds to this branch that goes up to the right. So the limit as x goes to positive infinity of this function is also positive infinity. Okay, now what happens as x goes to negative infinity? So that would be represented over here. Negative 3 times a really large negative number. That's going to be a really large positive number. Okay, now negative 5 doesn't really do much to it. It's negligible. So we still have a large positive number in the numerator. And then if we divide it by negative 3, we're going to get negative infinity. Okay, so that's where negative infinity comes here. And that, of course, is represented by this branch right here, goes down to the left. So our algebraic solution matches our graphical solution. Okay, all right, so we will stop right here. These are some of the examples that you might encounter on your homework. You might encounter something very similar or something slightly more different in terms of just different numbers, not different concepts. Okay, if you encounter any problem that you're struggling with, definitely let me know. Okay, all right, thank you all for watching, and I will talk to you next time.